Today's lecture is lecture 30, 10.1 to 10.2, Introduction to Intermolecular Forces. So we know that chemicals can exist in three different phases of matter. We have gases, we have liquids, and solids. So the difference between these individual phases of matter have to do with the forces that hold these molecules together. So for solids, we have a very strong force holding all of the molecules together. In liquids, we have a moderate amount of force holding our molecules together. And then in gases, we have little to no intermolecular forces actually holding these gas particles together. So they're free to move throughout whatever volume they occupy. And so we need to introduce the idea of these intermolecular forces that hold together our molecules to give us our different phases of matter, our gases, liquids, and solids. So we need to, in order for us to understand these intermolecular forces, we first need to go back to one of our seminal concepts in general chemistry, which is electronegativity. So if you recall, electronegativity is the tendency for a bonded atom to attract electron density towards itself. And so this is not the electron affinity, this is the ability of a bonded atom to attract the density to itself. And so furthermore, when you have bonding between two different atoms, covalent bonding, you can either have our electrons being shared equally as a nonpolar covalent bond, or you can have your electrons shared unequally with a polar covalent bond. And the difference between the nonpolar and polar covalent bond depends on the electronegativity of the two atoms that are sharing electrons. If you have a highly electronegative atom that is bonded to a low electronegativity atom, you're going to see the electron density is going to be located over the highly electronegative atom. And so what you have left there is a partial negative around the highly electronegative atom and a partial positive charge around the lower electronegativity atom. Conversely, if you take a look at your nonpolar covalent bond, this would be bonding between two atoms of similar electronegativities, such that the electron density is shared equally between the two. So let's remind ourselves which of these covalent bonds is most polar. So pause the video for a second and take a look and identify the most covalent bond. Okay, so we should be able to identify that CF is going to be our most covalent bond. So the reasoning between that, if we take a look at our periodic table, we can see that the difference, the physical difference on the table between carbon and fluorine is the largest among all of these atoms involved. Therefore, that large difference in electronegativity is going to give us our most polar bond. But in fact, if we take a look, we can see that all A, B, and C are all going to be polar covalent bonds, even though CF is the most polar, whereas F2 is going to be nonpolar covalent. Okay, so since we recall our ability to assess whether an individual chemical bond is polar or nonpolar, we can now extend this understanding to a molecule as a whole. And so this introduces the idea of a dipole. So a dipole is a chemical bond with a positive end and a negative end. And so charges are indicated by our lowercase sigma and the charge. And so the dipole is shown by a cross arrow, where the positive end is on the positive atom and the arrow points to the more negative charged atom. And so dipoles are easily displayed using our electrostatic map. So we can see here that for this chloromethane molecule, CH3Cl, we can identify our electronegativity of all of our individual atoms. So instead of taking a look at these pictures on the slide, let's actually draw this guy up here on the board. So if we see our carbon, and we have this tetrahedral sort of structure, where we have our three hydrogens on the bottom, and then we have our chlorine here on the top. And so if we take a look at the electronegativity of each individual bond here, so we have our CH bonds are going to be nonpolar covalent. All right, so there's not going to be any net charge or dipole on each of these individual CH bonds. But we do know that CCl bond is going to be a polar covalent bond. Whereas we have our partial negative charge on our chlorine because it's the more highly electronegative atom, and we have a partial positive charge on our carbon because that is the less electronegative atom. So we can draw the dipole moment of this entire molecule with a plus sign on our partial positive atom and the arrow pointing to our region of higher electron density, our partial negative. Okay, so instead of just talking about an individual bond itself, this idea of a dipole, and so this directional arrow here is called a dipole moment, which is talking about the overall um, dipole nature of a molecule in general. This dipole moment will tell us the overall charge of the molecule. So we can see this bottom part of the molecule is going to have a partial positive charge. The top part of the molecule is going to have a partial negative charge. So if we go back to our slide now, we can take a look at the electron potential map, the color image here, and we can see that that in fact is true. As we go from our partial positive on the lower side of our molecule up to our partial negative on our top of the molecule, we can see the electron density of the molecule as a whole. And so we can see that this chloromethane molecule, CH3Cl, is in fact acting like a magnet, where we have a negative pole here on the top and a positive pole on the bottom of the molecule. Okay, so we're not introducing any new concepts here. We're only just extending our understanding of polar covalent versus nonpolar covalent to a molecular scale. So now let's take a look at molecules that incorporate lone pairs of electrons. So we have ammonia here, which is NH3, and we have our lone pair of electrons on the top. And then we have water here, which has H2O, and then two sets of lone pairs. So if we think about the overall charge or the overall dipole moment on this molecule itself, we see that each of these individual covalent bonds are themselves polar, but then we also have our lone pair of electrons too, which carry this negative charge. Okay, so these lone pair of electrons are actually more of a negative charge than our polar bonds because they're electrons, which carry a full negative charge. Okay, so if we take a look at, so let's take a look at ammonia. So best to take a look up here on the board. And so if we take our N in the middle, and this is going to be trigonal pyramidal. So we have our nitrogen, and then we have three hydrogens, and then we have our lone pair of electrons on the top. So we can identify that each of these individual NH bonds are going to be a polar bond, where you have a positive side, a partial positive on the hydrogen, going to a partial negative on the nitrogen in the middle. So each of these individual NH bonds are going to be a polar covalent bond. And then we have our lone pair of electrons, which is going to be a polar, put a net negative charge straight upwards. So what we have here is the summation of our vectors. Okay, so if you have an experience with physics, you will know how to sum vectors together. So if we take a look at, so just a quick sort of review of vectors. So vectors have magnitude and direction. So if you have a vector going upwards and a vector going to the side, if you add these two vectors together, you're going to have a net vector that goes into the middle. So this vector in the middle, so if we say addition of A plus B is going to equal our vector C. Okay, so you add the directionality together to get the total net vector. So what we have here, these net dipole moments here, we have a three-directional diagonal vector between these three NH bonds. So if I grab a couple of my pens, we can sort of visualize what's going on here. So if we have, so hopefully you can see here on the camera, so we have a trigonal pyramidal sort of structure. Okay, and so each of these, so if we think about on a Cartesian coordinate, a three-dimensional coordinate, where we have X, Y, and Z. So hopefully you can see that each of the X and Y dimensions of this trigonal pyramidal structure are going to cancel each other out. The next vector that's going to be remaining is going to be going straight upwards. Okay, so the X and Y dimension of all of these bottom trigonal pyramidal are going to cancel each other out, leaving us just a net dipole moment going straight upwards. And so that upwards dipole moment is going to add with the dipole moment of our lone pair electrons to give us a net dipole moment for the molecule, partial positive on the bottom, partial negative on the top. Okay, and if you need any more clarification for that, I'd be happy to review that more in person during our recitation period. Okay, next I want to take a look at water. So water has a structure of H2O. So you have our oxygen, our two hydrogens. We know this has a bent structure. And then we have two different lone pairs. And so we can identify again that each of these OH bonds are going to be a polar covalent bond, where you have the partial positive side on the hydrogen and the partial negative side on the oxygen. And then we have our two lone pair of electrons, which each carry a net negative charge to them. So here, a little easier, we can see the summation of our vectors here for each of these OH bonds. So these diagonal OH bonds are the summation of a vector going straight upward and a vector going sideways, a vector going straight upward and a vector going sideways. So you can see that these two vectors that go from left to right and right to left have the same magnitude but opposite directions. So therefore, these two vectors are going to cancel each other out in this x dimension. All that's left now is our z dimension going straight up and down. We can see both of these vectors are going to add together, giving us a dipole moment for the OHO bond going straight upward, with a partial positive on the bottom and a partial negative towards the top. And then again, we can see these two negative charges due to our lone pair electrons are each going to have a dipole moment going outward. And again, we can see that our left and right x coordinate vectors are going to cancel each other out, leaving us just again with an up and down dipole moment. So when we sum these two dipole moments together, we can say the net dipole moment for this entire molecule of water is going to be positive on the bottom and negative on the top. So partial positive, partial negative. Okay, so this is what makes ammonia and water polar molecules. So if we go back to the slide and take a look at the artist renderings for ammonia and water, we can see that the net dipole moment for ammonia, in fact, goes straight upwards towards the lone pair, and the net dipole moment for water goes diagonally right through the middle of those two lone pair of electrons. So not all molecules that include polar covalent bonds are in fact polar molecules. So they don't all have a dipole moment. So for example, if we take a look at carbon dioxide, CO2, we can see that each of these individual CO bonds are in fact polar, but they are going in the opposite direction. So we have our positive on the carbon and our negative over in the oxygen. Since this is a linear structure, we can see we have two different vectors of equal magnitude going in the opposite direction. So those two are going to cancel each other out, which the net that we have is no dipole moment, and therefore the molecule is nonpolar. Same idea here for this tetrachloromethane, CCl4. We can see that each of these individual CCl bonds are going to be polar, but when we sum all of their vectors together, we can see the net dipole moment for tetrachloromethane is in fact zero, a nonpolar molecule. So we can explain this concept of polarity of a molecule, this dipole moment. We can assign a numerical number, a D, a dipole moment, to indicate how polar a molecule actually is. So the higher this dipole moment number D, the more polar the molecule is. So when we take a look at many different molecules here, we can see that when we're dealing with ionic salts, the dipole moment is absolutely enormous because we're dealing with charged particles. And then when you get to your molecules, you can see that the more lone pairs that you have and the more polarity that you have, the higher your dipole moment is going to be. And then our nonpolar molecules, CO2 and CCl4, have a zero dipole moment. Okay, so sometimes, so we have up to this point, we've taken a look at kind of simple molecules where the dipole moment goes right through the center of the atom itself. But not all molecules are as straightforward. So, for example, if we take a look at vinyl chloride, which is C2H3Cl, we can see that the molecule has this sort of 3D structure to it, where we have a trigonal planar shape around each of our individual carbons. So we can identify that each of the CH bonds are going to be nonpolar, but that CCl bond is going to be highly polar. So therefore, if we take a look at the net dipole moment of this molecule in general, you'll see that the dipole moment travels in the direction of that CCl bond. That's because each of these CH bonds are not going to contribute to the overall summation of the dipole moment for the molecule. So we can draw our partial positive here around that carbon and our partial negative centered around the chlorine. So we can see our dipole moment does not actually travel through the center of the molecule. It's a little bit cockeyed. And we can see that in our 3D heat map structure as well. All right, so your turn. So I'd like you to pause the video and draw the dipole moment for methanol. And so just in case that you guys are struggling with drawing the proper 3D structure for methanol, that's going to be a carbon in the center. And then we'll have our tetrahedral sort of shape around this carbon with 3 H's. And then going up, we'll have an oxygen with 2 lone pairs and then a bent structure to our hydrogen. All right, so pause the video and determine the polarity and draw any dipole moment for methanol. Okay, let's take a look. So if we identify all of the first step is to take a look and identify any sort of bond polarities that we have for each of our different covalent bonds. So each of our CH bonds, those guys are going to be non-polar covalent bonds. So they are not, we do not need to draw a dipole for any of those individual bonds. For our CO, we know that that is going to be a polar covalent bond. And since oxygen has a higher electronegativity than carbon, we know that we have a partial positive on carbon pointing to our partial negative on the oxygen. We know that oxygen-hydrogen is also a polar covalent bond, so we're going to have a partial positive on the hydrogen pointing to our oxygen. And then we have 2 lone pairs. We know that dipole moments face away or face towards those lone pair electrons. So if we sum all of our vectors together, we have our CO and our OH are going to be facing together. So if we sum our vectors together for these 2 guys, you'll see that our vectors that are facing each other are going to cancel each other out, leaving a net vector going straight up through the center of that oxygen. The same idea for these lone pairs. If we cancel out their sideways vectors and only add together their vectors going in the same direction, we can see that our net dipole moment for the entire molecule in general is going to be partial positive at the base of our oxygen, and then a partial negative facing right through the directionality of that oxygen, right cutting through the middle of the COH bond and right through the middle of our 2 lone pairs. Okay, so if we were taking a look at our heat map here, we would see a large electron density on top of the oxygen around our lone pairs and an electron deficiency down here towards the bottom of the molecule. So we have a dipole moment that travels not through the center of the atom, but through the center of that electronegative, or excuse me, not through the center of the molecule, but it does travel right through the center of our most electronegative atom, oxygen. Okay, next. Let's take a look at this clicker question here that states, which of the following molecules would you expect to be the most polar? Okay, and so each of our individual, we have a CH3 on the bottom of each of our molecules. And then, so this top one here is an additional CH3. This one here is a nitrogen with two hydrogens. This guy here is an oxygen with one hydrogen on. And then the last one is a sulfur with one hydrogen. So pause the video and think about that for a moment. Okay, so the correct answer here is C. So the answer here lies in the number of lone pair electrons. So we can see that our C2H6 here, that's actually going to be a non-polar molecule in general. There's no polar covalent bonds here, so that one's out. Our CH5N is going to be a polar covalent bond going straight upward through this nitrogen, but there's only one set of lone pair on this nitrogen. Whereas on the oxygen and sulfur, we have two sets of lone pairs. So the more lone pairs that you have, the more polar the molecule is going to be. So therefore, that knocks out B. So now we have to compare between oxygen and sulfur, the compound containing oxygen and sulfur, which one is going to give us a more polar molecule. So since they both have the same number of lone pairs, we need to turn next to which of these atoms, oxygen or sulfur, is a higher electronegativity atom. And we know that oxygen is our second highest electronegativity atom. Therefore, the correct answer has to be C. Okay, so now that we've introduced this idea of dipole moments and molecular polarity, now we can start to get into the idea of why molecules are attracted to each other at certain conditions and why molecules are not attracted to each other at other conditions. For example, if we take a look at nitrogen, N2, we can see that the molecules are weakly attracted to one another at low temperatures. So we can see that as liquid nitrogen. But when we get to higher temperatures, the intermolecular forces are no longer able to keep it together, and we can see that N2 evaporates out as our N2 gas. So why is it at certain temperatures that we have certain intermolecular forces that hold us together in one phase of matter, but at other temperatures we see a different phase of matter? Same thing for boiling versus freezing versus liquid state of water. What are the forces that define these individual phases of matter? So this brings us to intermolecular forces. So I've been teasing this concept the whole lecture. Let's really delve into it now. So intermolecular forces are interactions between molecules that hold them together. These forces are electrical in origin and result from the mutual attraction of unlike charges or the mutual repulsion of like charges. Okay, so we can think of these, so by stating that these forces are electrical in origin, what we mean here is throughout the semester, hopefully you've noticed that we keep referring to molecules as magnets, okay, having positive poles and negative poles of magnets. And we know that when we put like sides in the magnet, so two positives or two negatives together, we know we have repulsion. But if we put opposite poles of a magnet together, a positive and a negative together, we know that we have attraction. So we've just introduced this idea of polarity, dipole moments for molecules themselves. So since these molecules can act themselves like magnets, we can either have attraction of our opposite poles of our magnets, of these molecules, or we can have repulsion by putting together the like charges of our molecular magnets. And so our different types of intermolecular forces are ion dipole forces, and then a classification called the van der Waals forces, which encompass dipole-dipole, London dispersion, and hydrogen bonding. So we're going to go through all of these individual intermolecular forces and say how those actually help to determine our attraction between molecules. First off is the ion dipole forces. So these are interactions between, so these are the result of electrical interactions between an ion and the partial charges on a polar molecule. So what we can see here is an attraction here between an ion itself, so whether it's a negatively charged anion, so think about Cl minus or F minus or O2 minus, okay, or a cation, so think about sodium plus, potassium plus, magnesium 2 plus. So these are talking about ions in the center, so an attractive force between a free ion and then a molecule. So this would be, for example, this CH3Cl that we just worked through has a dipole moment to it that has a partial positive and a partial negative charge, okay, or water or ammonium. So this would be a lineup of our molecule with a partial positive and partial negative charge, and attraction between the opposite polarity of between the ion and the partial positive, partial negative of a polar molecule. Okay, so if we're talking about H2O, for example, the attraction here would be between a negative ion and then the two hydrogen side of a H2O molecule, the partial positive side. Whereas on this side, we would have attraction with the positive ion with our oxygen side of our H2O, our partial negative. So you would align our polar molecule such that it has an electrostatic interaction between that ion and the polar molecule itself. All right, so this is called ion dipole interaction or ion dipole forces. And it's easy to remember because it is an interaction between a free ion and then a molecule which has a dipole. The next interaction is called dipole-dipole interaction. So this is the result of electrical interactions among dipoles on neighboring molecules. So you can see here when we have our molecules, each of them with a dipole moment, so a partial positive and partial negative, if each of these molecules are lined up in a highly ordered fashion, we can have an attractive interaction between partial positive and partial negative, and partial positive sides of our molecule. So these individual molecular dipoles can attract each other. On the flip side, we can also see a net repulsion if they are organized in a fashion where our partial negatives are close to each other and our partial positives are close to each other. So this dipole-dipole interaction, it's sort of a balancing act between the highly structured faction or highly structured order that has attraction versus our sort of random disorder that can have more of a repulsion. So it's a balancing between the two. So these dipole-dipole forces here can excuse me. The stronger these dipole-dipole forces, the stronger the interaction that you'll have holding together a set of molecules. So the higher the dipole moment that we see, so the stronger each of those individual magnets are going to be, the stronger the interaction that's going to hold them together. So as the dipole force increases, the intermolecular force for the dipole-dipole interaction increases. As the intermolecular forces increase, the boiling point increases. So if we think about a different or three different molecules here, each of them we can see has an increasing dipole moment. So that means that if we go back and take a look at this dipole-dipole interaction, the force, the electrostatic force, so the higher the dipole moment, the higher that D term, the stronger the interaction holding together these molecules, holding them together is going to be. Okay, so as we go to higher dipole moments, these molecules are going to be held stronger together. And so we can observe here that the stronger that intermolecular force that's holding it together, the higher the boiling point becomes. Okay, so let's conceptualize this for a second. Why is that true? So if we go up here on the board, we can take a look at if we have a liquid solution. And so let's think about water. Okay, so water, we have our H2O. And so we know that our hydrogen side is going to have a partial positive charge and our oxygen side is going to have a partial negative charge. So when we line these guys up in a highly ordered fashion, we can see that there can be a dipole-dipole interaction that will hold these guys together. We'll also show later on that there's hydrogen bonding as well, but there's also this dipole-dipole interaction. And so we have our partial positive and partial negative is going to kind of hold this guy together. So we know that, so this is water in the liquid form. So liquid water has a strong force holding those water molecules together. When we see evaporation or boiling, what we see now is our H2O molecules are going to then be free out in the air with no intermolecular force holding them together. So in order to boil, in order to go from these intermolecular forces out to the gas phase, what we have to do is we have to apply enough energy to break the intermolecular forces that are holding these individual molecules together. So the way that we break these intermolecular forces is by adding heat, which is thermal energy. So we can do that at our houses by putting our water on the stove and adding heat to it. So as we add more energy, as energy comes into the system, we can overcome the energy, the attractive force that's holding these molecules together that can break that interactive force and cause those water molecules to escape out as gas. So it makes sense that the stronger the intermolecular force interaction that holds these molecules together in liquid form, the more temperature, the higher the heat that we have to add in order to break them apart into gas. So therefore, the higher the boiling point. So this is a very important concept here. The stronger the intermolecular force, or the higher the dipole force, the stronger the intermolecular force, and therefore the higher the boiling point. And so this will be the case for all of our different types of intermolecular forces, whether we're talking about ion-dipole interactions, dipole-dipole forces, London dispersion forces, which we're about to get to, or hydrogen bonding. That's a very key concept. The next force we're going to talk about is London dispersion forces. So this is the result of motion of electrons, which gives a molecule a short-lived dipole moment, which induces temporary dipoles in neighboring molecules. Okay, excuse me, before I get onto this London dispersion force, the only thing I wanted to go back and reiterate here about dipole-dipole interactions is that not all molecules can undergo dipole-dipole interactions. And really, for that matter, not all molecules can undergo ion-dipole interactions. In order to undergo either ion-dipole interactions or dipole-dipole interactions, the molecule itself has to have a dipole moment. So it has to be a polar molecule. If you're dealing with a nonpolar molecule, there would be no partial positive and no partial negative. So therefore, ion-dipole and dipole-dipole interactions are only observed in polar molecules. That's very important. Next, this London dispersion forces, which we discussed, is a result of the motion of electrons within a molecule in order to give a short-lived dipole moment, which induces temporary dipoles in neighboring molecules. So these London dispersion forces, this is very important to note, can be observed in any molecule, no matter what. They can even be observed in a single atom. Okay, so any single molecular or atomic structure can have a London dispersion force. And so what we see here, this London dispersion force comes into play specifically when we're thinking about nonpolar molecules. So if we think about bromine, Br2, this is a nonpolar covalent molecule. There is no net dipole moment that exists at all times for bromine. But what we can think of is so we know that electrons exist within molecular orbitals. And so molecular orbitals, there's a probability distribution stating where those electrons are likely to be at any given point in time. And so this heat map distribution here just shows on average where do the electrons actually exist at a given period of time. But those electrons can go wherever they want to. So therefore, at a period of time, for an instantaneous moment, there could be a case where both of the bonding electrons are located closely located to one of the atoms, which would give that individual atom a temporary partial negative charge, which would in turn leave the other atom with a temporary partial positive charge. At that point, you would produce what's called a temporary dipole. And in that moment, it could have an interaction with another molecule that is also observing a temporary dipole at that moment. So this is just a fleeting formation of a magnet that could go back at any moment. So you can see that this London dispersion force would not be as long lasting or persistent as our dipole-dipole interactions that are observed with polar molecules that have a dipole at all times. This is just a momentary interaction between our neighboring molecules that are forming this temporary dipole. So, like I said, all molecules, whether they're polar or nonpolar, can have their electrons sort of fluctuate where they're actually located within the molecule, and they all can have what are called these London dispersion forces. Okay? And so, again, the sort of idea here, as the London dispersion force increases, the intermolecular forces increase, and therefore, as the intermolecular forces increase, our boiling points increase. This is the same idea that we observed previously. So one key factor that we observe here for London dispersion forces is as the molecular weight of the molecule itself increases, we can observe that the London dispersion force also increases. Okay, so we can think of this in terms of if you think of the size of a golf ball versus the size of a tennis ball versus the size of a bowling ball. So if we go up on the board, we draw our golf ball, our tennis ball, and our bowling ball. Okay, so if we think about the relative size, so forming temporary dipoles in each of these individual molecules. So if we see our bonding electrons for our smallest molecule here, so golf ball, tennis ball, bowling ball, really think of this actually as size of molecules. So better yet, let's think of this as F2 and Cl2 and Br2. Okay, so these diatomic molecules that are increasing in size. So for our smallest molecule, F2, if they form a temporary dipole where you have a partial negative and partial positive on one side, and if each of these guys all form their temporary dipoles, partial negative, partial positive. So the further apart that you separate these individual charges, the stronger the magnet is going to become because it's not going to be canceled out. The charge is not going to be canceled out by its partner. Okay, so the magnitude of the overall London dispersion force on smaller molecules is going to be small. And it's going to become larger and larger when we're talking about larger molecules. Okay, so the bigger the molecule, the larger the molecular weight, the stronger the London dispersion force becomes. And the reason is because those partial positive and partial negative charges are further spread apart in physical space. So they have more of an opportunity to act as a magnet. So if we go back to the slide here, we can take a look and see that as we go from F2 to Cl2 to Br2 to I2, as we increase our molecular weight, we can see that our boiling point becomes higher, and for that matter, the melting point also becomes higher as well. Okay, so the same sort of idea if we were talking about we had to add heat to overcome our liquid to turn to a gas form, the same sort of thing occurs when we're talking about melting point. We have to break some of our intermolecular forces to go from a solid to a liquid. Okay, so melting point and boiling point both scale with the strength of our intermolecular forces. Okay, so we've identified that the London dispersion London dispersion forces scale with the molecular weight of the individual molecule. The London dispersion force also scales with the compactness of the molecule. So here we have pentane and 2,2-dimethylpropane. So these two molecules have the exact same molecular weight, but we can observe that they have two different boiling points. And so we can see that the pentane, which is a more spread out structure, a less compact structure, has a higher boiling point than the 2,2-dimethylpropane, which is a more compact structure. So the same sort of rationale exists for this phenomenon here. The more spread out the molecule is, just like the higher the or higher the molecular weight, the more spread out the molecule is, the further apart our partial negative and partial positive poles could be on this specific molecule. So therefore, the higher the London dispersion force. So London dispersion force increases with molecular weight, and it also increases with the less compact or more spread out the molecule is. Okay, next let's move on to hydrogen bonding. So hydrogen bonding is an attractive force between a hydrogen atom bonded to a very electronegative atom. So it's only an oxygen, nitrogen, or fluorine, and an electron-rich region elsewhere in the same molecule or in a different molecule. Okay, so what you're going to observe here is this hydrogen. So this is most often the electron-rich region is an unshared electron pair on another electronegative atom. So what we're going to see here is our hydrogen bond is going to be a straight line bond between a hydrogen that's bonded to an electronegative atom. So this has to either be an oxygen, nitrogen, or a fluorine. So hydrogen that's covalently bonded to an oxygen, nitrogen, or fluorine forms a straight line intermolecular force to an electron-rich region on a neighboring electronegative atom. So typically that's a lone pair on a neighboring electronegative atom. Okay, so we'd see this straight line form between the oxygen to a covalent bond to the hydrogen, and then the hydrogen bond intermolecular force to that lone pair of electrons. So we have that partial positive on the hydrogen, and then the negative charge on those electrons on the neighboring oxygen. And the same sort of thing here we can see with ammonia. We have a straight line between our nitrogen bonded to the hydrogen, straight line hydrogen bond to the lone pair on the neighboring ammonia molecule. All right, so these both show a hydrogen bond between like molecules. You can also have hydrogen bonding between unlike molecules. Okay, so this is a very strong electrostatic interaction. And so at this point, I also want to make sure everyone is very clear here. Even though we call this a bond, it's not actually a true covalent or ionic bond. There's no electrons being transferred or shared here. This is just an electrostatic interaction here. So we have a positive and a negative that are electrostatically being held together. It's not actually a covalent bond. No electrons are being transferred here. This is just an attractive force. Okay, so hydrogen bonds are really a strong interaction. So these hydrogen bonds between water are what actually allow water to be in a liquid form at our normal temperatures here on Earth. So we have this network of hydrogen bonding between all of our individual oxygen molecules. And we also see hydrogen bonding within the DNA within all living species here on Earth. So we have our four different nucleic acids within our DNA, deoxyribose nucleic acids. And so each of our different base pairs here are going to be held together by either two or three hydrogen bonds between those side groups on these base pair units. So hydrogen bonds are actually entirely essential to life as we know it on Earth, keeping DNA and water together. Okay, and so if we take a look at the boiling points of several different compounds going down a specific group, so CH4, SiH4, GeH4, SNH4, and then we take a look, NH3, PH3, ASH3, SBH3, et cetera, we can see that we have, so take a look to the boiling point for each of our different groups. We can see that our NH3, H2O, and HF boiling points are higher than expected when taking a look at the trend of the other molecules. Okay, as we move downward on our periodic table. The reason is that for those boiling points to be so high is because of the hydrogen bonding present when you have hydrogens bonded to our highly electronegative atoms of nitrogen, oxygen, and fluorine. And if we think about for a second, why do we actually observe an increasing in our boiling point as we go to lower on our periodic table for the other atoms? That should be identified by our presence of our London dispersion forces. As we go lower in our periodic table, we can see that the molecular weight is becoming larger. Therefore, our London dispersion forces are going to be stronger. But we can see here that for our NH3, H2O, and HF, those hydrogen bonds are actually such a strong force that it can way overcome the strength of those London dispersion forces. Okay, so now comparing our main types of intermolecular forces, we have our ion-dipole interaction, which the strength is highly variable, and that occurs between free ions in solution and polar molecules that have a dipole moment. We have the dipole-dipole interaction, which are typically sort of moderate to weak forces, which occur only between polar molecules. We have our London dispersion forces, which can be extremely weak, or they can be pretty strong, actually. So, kind of in the middle sort of forces, depending on the size of the molecule. So, if you're dealing with a very, very large molecule, the London dispersion force can be really, really strong. But if you're talking about small, compact molecules, London dispersion forces are actually pretty weak. And so these occur for all individual molecules, but the strength depends on the size of the molecule or how compact that molecule is. And then you have hydrogen bonding, which is our strongest of all of our forces here. And so these occur only between molecules with hydrogens that are bonded to highly electronegative atoms, oxygen, nitrogen, or fluorine. So if we're ranking these and ranking these intermolecular forces, our van der Waals interactions by list of strength, you would typically think of London dispersion as being the weakest, dipole-dipole interaction as being the second weakest, and hydrogen bonding as being the strongest interaction that will hold a specific set of molecules together. And we know the stronger the intermolecular forces, the higher the boiling point or the higher the melting point. Okay, so now let's go through and let's identify the individual intermolecular forces present for each different molecule and then indicate which one would have our strongest forces, which would indicate the highest melting point and highest boiling point. Okay, so for these guys here, we're going to pause the video and take a look here and identify which do you think are going to be our strongest intermolecular forces. Okay, so if we take a look at this example here, we can see CO2. This guy is a nonpolar molecule. So nonpolar molecules can only have London dispersion forces. C6H6, again, is a nonpolar molecule. We have no net dipole moment. So again, there's only London dispersion forces. C3H6O, we can see has a net dipole moment that goes through that oxygen. So that has London dispersion forces and dipole-dipole interaction. So there's two types of intermolecular forces for this molecule, whereas the other two, which only had one, the London dispersion force. Finally, if we take a look at C4H10, we can see this is another nonpolar molecule, so it only has London dispersion forces. So since A, B, and D only have one type of intermolecular force, whereas C has two types, the dipole-dipole interaction and our London dispersion force, the correct answer is C. C has the strongest intermolecular forces because it has two different types of intermolecular forces present. Next, in which of the following are London dispersion forces not the only forces at play? So pause the video and take a look. Okay, if we take a look here, so krypton. So here we don't have any covalent bonds present. So this one only would have London dispersion forces. CH4. This guy here is a tetrahedral structure. That's going to be a nonpolar molecule. So that one only has London dispersion forces. NH3. We know that this guy is going to be trigonal pyramidal and having a lone pair of electrons sticking out of the top. So therefore, we know that this guy is going to be a polar molecule. Therefore, it'll have London dispersion forces. It will also have dipole-dipole interaction. And since we have hydrogens bonded to a nitrogen, we know that this guy is also going to have hydrogen bonding. So you're actually going to have three different types of intermolecular forces for NH3. Okay, so even though we know C is going to be our right answer, let's take a look at our last two. We have AlCl3. That guy is going to be sort of a trigonal planar sort of shape here, a nonpolar molecule. And then we have a CBr4, which is going to be tetrahedral, again, a nonpolar molecule. Each of those D and E are going to be a London dispersion only. Next, let's take a look at these four molecules and determine which of the following has the highest boiling point. All right, take a moment to look at this. Okay, so we know that to increase our boiling point, we need to increase the strength of our intermolecular forces. So we know the more intermolecular forces that you have, the higher the boiling point is going to be. So if we take a look at all four of these compounds, we can see all four are polar, and three of them have an OH. So we know that the three ones that have an OH and are polar are going to have London dispersion forces, dipole-dipole interactions, and hydrogen bonding. Whereas this guy with an SH only will have London dispersion forces and dipole-dipole interactions. Remember, hydrogen bonding is only with a hydrogen attached to an oxygen, nitrogen, or fluorine. So we know that B has to be out as our lowest boiling point here because it only has two intermolecular forces instead of three. So now if we take a look at these three remaining ones, we take a look and we see there's actually A has two different opportunities for hydrogen bonding, whereas C and D only have one opportunity for hydrogen bonding. So therefore, since even though A, C, and D all have all three types of intermolecular forces, since A has the ability to hydrogen bond two times, therefore that's going to be our highest boiling point because it's going to have our strongest intermolecular forces. Next, which of the following has the highest intermolecular force? All right, pause the video, take a look. Okay, so here we can identify that if we take a look at A, this is a nonpolar molecule, no net dipole moment. So therefore, this guy would only have London dispersion forces. B, we can see that having an oxygen here, that's going to force this to be a polar molecule. So therefore, we're going to have a net dipole moment, which would mean that we would be able to have London dispersion force and dipole-dipole interaction. Since there's no hydrogen attached to this oxygen, we know that it cannot have hydrogen bonding. So this guy has two different types of intermolecular forces. Finally, if we take a look at N2, we can see that this again is a nonpolar molecule. So we only have London dispersion forces. So since B has two different types of intermolecular force, whereas A and C only has one, we know that the correct answer here has to be B. Hopefully you're starting to get a little more proficient at working through these problems. Finally, or I guess we have two more examples. This one states, which of the following substances would you expect to have a higher boiling point? Okay, an Rn atom, O2 molecule, or Br2 molecule. So pause the video, take a look. Okay, so if we're taking a look here, we can see that we have two different sort of reasonings here that the correct answer here is going to be C. The correct answer is C because of two different things. One, Br2 is going to have our highest molecular weight. And two, if we take a look at the relative bond lengths here, we can see that Br2 is going to be the most spread out molecule. So even though A, B, and C all have just London dispersion forces, we know that the heavier the molecule and the more spread out the molecule, the higher the intermolecular force is going to be, and therefore the higher the boiling point. So correct answer is C. Our final question states, the intermolecular force responsible for increasing the boiling point of alcohols with increasing carbon atoms is what? So we have our H2O here, and then we have CH3OH, we have C2H H5OH, we have C3, what would that be? H7OH, and then we have C4, that would be H9OH, and we can see that we have our boiling point dips as we go from water to the CH3OH, and then increases steadily as we get to these further to the right on the table. So we ask the question, the intermolecular force responsible for increasing the boiling point of alcohols with increasing carbon atoms is what? So we're talking about these final four. What is the cause of this increase in boiling point? All right, so pause the video and think about that for a moment. Okay, so we see that each of these alcohol molecules have an OH. So each of them can undergo the same sort of hydrogen bonding. Each one of them is going to be a dipole. So each one has dipole bonding. But we can notice here that each of these guys has a higher molecular weight as we move to the right, and also they're more spread out. So therefore, the London dispersion force becomes a higher, a stronger force as we move further to the right on the table. Therefore, the correct answer is C. The London dispersion force is the intermolecular force responsible for increasing the boiling point of these alcohols. All right, that's it for today. Thank you for your attention.